Okay, so Plasma. Who here remembers Plasma? Well, we all should, because INTMAX is the next great thing, and INTMAX is a Plasma. But Plasma is an idea that actually has at least a 7-year history inside of the Ethereum space. It was actually one of the very first layer 2 scaling solutions that we started looking at, and even before we looked at rollups, and this was at the time when we were still looking quite a lot at state channels and many different kinds of options. And so Plasma is a scalable layer 2 design, right? And the big difference between Plasma and rollups is that Plasma requires only O of 1 data on chain. So what this means is no matter how many users there are, you only need to publish a fixed amount of data on chain in order to have a Plasma system. So rollups, for every transaction, you need to put some number of bytes on chain. For Plasma, you only need to put hashes. You only need to put one hash of everything that happens on chain. Now, what are the trade-offs? Plasma is not fully general purpose. Plasma is in this complicated space where it's more general purpose than state channels. So state channels actually do not require putting any information on chain at all, except when people deposit and withdraw. But Plasma does require putting a little bit of information on chain. And what you get for it is that it works for payments, and it works for many other applications, but it is not fully general purpose. So Plasma by itself cannot run the EVM, at least with the same kinds of unconditional security guarantees that you can get with a rollup. So Plasma works perfectly for payments. It does not work, at least unconditionally, for a very general purpose EVM. And what you can do in the middle, it's complicated. And over the last 5 years, the space of things that you actually can do with these Plasma designs has actually improved quite a bit. So let's talk about how Plasma works, right? So the way that Plasma works is that every time there is a Plasma block, you create a Merkle tree. And you can think of the Merkle tree as being like dealing with individual coins, right? So basically think of every single object that's being traded inside of Plasma as being like a separate NFT. Even if you have, let's say, 3 ETH, then each ETH it becomes a separate NFT, and you have 3 NFTs. So every time there is a block, what happens in the block is you create this Merkle tree, and in every NFT has an associated index, and at that position in the tree, if there is a transaction at that position, you put the transaction in the tree. If there is not, you put a 0 in the tree at that position. Right, so over here, for example, one example is you have coin 1 going from Alice to Bob, and that's put in position 1 in the tree because positions start with 0. You have coin 4 going from Charlie to David. The transaction is put in position 4 in the tree, and so on. So every time you have a Plasma block, you have this tree, and only the root of the tree gets published to the chain. Then later on, you might have a different tree. And if that different tree transacts with the same coin, you get a transaction in the same position. If it transacts with a different coin, you have a coin in a different position. So let's, if you look at this example, imagine that these are the last 3 transaction trees in a basic Plasma chain. If you assume everything before that is valid, then what do we know about this? In this case, we know that Eve currently owns coin 1, right? Because here you have on the left, a transaction of coin 1 from Alice to Bob, and then on the right, a transaction of coin 1 from Bob to Eve. Then we know that David owns coin number 4 because there's only one transaction in position 4, and that transaction is going to David. And George owns coin 6 because there's only one transaction that's moving coin number 6, and it's giving it to George. So this is like a very simple model, but this by itself basically already is a Plasma system. So what's interesting about this? If you zoom in to any one specific coin, and you ask the question, who is the owner of that specific coin? Who is the person who deserves to have that coin right now? You do not have to look at that tree. You only have to look at the Merkle branches of one particular index. If, for example, you want to learn who is the current owner of coin number 1, you just look at the Merkle branch in the tree of position 1 in every single one of these plasma blocks. And so if you have some situation where people are disagreeing and you're trying to figure out who is the real owner of some coin, there's like only a very limited amount of information that you have to look at. So this Plasma, so it relies on this mechanism that's called a challenge mechanism, right? Basically, yeah, what happens is, if you have one of these coins, so let's say you are George, you want to exit coin number 6, so you have coin number 6 inside of Plasma, you want to withdraw, you want to get back 1 ETH, right? What do? You publish an exit message on chain that says, I have coin 6, I'm withdrawing it. Now, what if someone disagrees with you, right? So, for example, let's say, yeah, over here, you are Bob, and you received coin number 1, and you have proof that you received coin number 1, and you decide, well, I'm going to try to withdraw coin number 1. Now, Bob is not actually the owner of coin number 1, because in a later block, Bob already sent that coin. And so we have a challenge mechanism. The challenge mechanism basically says, this is called a not latest owner challenge. Basically, Eve, who actually has that coin, can challenge and say, well, no, here is a transaction that you signed that gives the coin away, and so that coin is not actually yours. There's 2 other challenges. So there's an invalid history challenge, where basically, you're saying, hey, this is the operator trying to trick the system, and you made this coin out of thin air, and then the operator has to prove that they didn't. There's also a double spend challenge. So basically, any way in which the user could cheat, or any way in which the operator could cheat, there's a challenge mechanism where you can provide evidence to show that they're wrong, and to show that actually you deserve to have some particular coin. So what's interesting about this design, right, is that it works by splitting objects up into individual coins, and it basically splits up responsibility, right? If, for example, you are George over here and you have coin number 6, from your point of view, you don't actually have to care who takes coin number 4, right? Because no matter what happens, whatever happens in coin number 4, you can only withdraw coin number 4 once. Coin number 6 is separate, right? So you get this very nice security property where only a few people need to even care about any specific piece of what's happening in the Plasma system. So these are the basic techniques, right? So I think and then if you want to extend these techniques to work well with fungible tokens, so work well with ETH, for example, then there's a lot of different ways to extend it. So basically, for an NFT, the history is always linear, right? Alice gives it to Bob, Bob gives it to Eve, Eve gives it to someone else. For a coin, you might have a graph. You might have 0.2 ETH over here, and they're coming from someone else, they came from someone else, they came from someone else, and then they actually came from 2 different deposits, and then you keep going back, right? And so basically, there are different designs. Here, to exit, you can provide the last week of history, and then you could challenge by showing that any part of that history is already spent. So there's a lot of ways to extend this design to work well with coins. Now, one of the challenges with Plasma back before, when people were really seriously thinking about this in 2018 and 2019, is that especially once you try to go beyond NFTs and you try to make this work first for fungible tokens like ERC20s or ETH, and then for decentralized exchanges, then for other applications, the challenge games become very complicated, right? Basically, when you're dealing with NFTs, the challenge games, you can fit them into one screenshot that I can put onto a slide. If you start making things more complex, then it just quickly becomes much more complicated, and there's a lot of limits to how much you can do. Since 2020, the big revolution that we've had is SNARKs, right? Basically, yeah, like actually using SNARKs and STARKs for everything. So, and what that lets you do is it lets you actually prove that that every single object that's being committed to chain is valid, right? So basically, STARKs let you prove that the operator of a chain is committing data that is correct. They could still be hiding the data, but it lets you prove that they're only committing data which is correct. Now, if we look at the types of challenges here, right? Basically, so the not latest owner challenge, that still exists. But then if you look at invalid history or double spending, those two types of challenges don't exist anymore. Because with SNARKs, there is no longer any ability for someone to commit invalid information to the chain. And so the complexity of even this challenge game goes down by a factor of, actually a factor of more than 3, right? I think a factor of 4. Because you go from 3 proofs down to 1, and the invalid history challenge mechanism is actually twice as complicated. So complexity goes down a lot if you use zk-SNARKs, and you also get some really interesting properties, right? Basically, if you have an operator and the operator is online, then what happens if, let's say over here, Eve decides that Eve wants to withdraw, and you see on chain that that block is the latest block, right? You have a guarantee that everything up to that point is valid, and you also have a guarantee that there cannot be any further spend because there are not any further blocks. And so when the operator is online, when the operator is not hiding information, when the operator is behaving honestly, there's actually no challenges that apply. And so Eve will be able to withdraw immediately. This is a big deal, right? It's a big deal because if you think about L2s right now, especially optimistic rollups, Arbitrum optimism, they're great, but withdrawing takes 7 days, right? And withdrawing takes 7 days, it's very annoying, nobody wants to take 7 days, and so people withdraw using liquidity providers, but then being a liquidity provider is also expensive, and like you start getting all of this complexity. With a Plasma chain, in the happy case, so where in any case where the operator is honest, you can just take your money out instantly. This is an incredibly powerful benefit. So rollups are still better because rollups, even in the unhappy case, they can also force instant withdrawals. But like this already is a very big deal, right? And I think it's important to really think about this, right? Because basically, Plasma was tried and Plasma was kind of given up on and replaced with rollups back in 2019 because in the context of only having fraud proofs, there was just so much complexity, there was so much limitation. In the context of having SNARKs and having validity proofs, all of that, most of that complexity and most of that limitation actually goes away. And to me, this is like the core reason for why the Ethereum ecosystem, I think, needs to go back to actually taking Plasma ideas really seriously. So challenges in generalizing to the EVM, right? So Plasma is designed around the assumption that each state object has a specific owner who cares about exiting it, right? So like we saw back in the examples, right? If you're George and you have coin number 6, you only care about coin number 6. You do not need to care about coin number 1. In the EVM, things do not really work this way, right? Also in Plasma, there's like in the EVM, there's no limits on dependency graphs, right? Something that happens in block n could depend on absolutely anything that happens in block n minus 1, right? The execution could just go anywhere, read this, write this, read this, write this, combine them together, and then write anywhere else in the chain. So all of this does make an EVM-based Plasma much less convenient. One solution that I suggested in the post that I made last year is to basically create a parallel state tree using UTXOs. So the way that this works is that you have a tree that is just a tree of like a state tree, basically accounts, account balances, account storage, exactly the same way that it works today. And then in parallel, you also have a separate data structure, and that separate data structure just looks like a graph of transactions, or even it could just look like a list of a list of trees a list of every individual way, like every individual tiny bit of ether that becomes its own NFT. There's efficient ways to do both of those, right? And so you basically have these two parallel states, and you use a zk-SNARK to prove that the two are equivalent to each other, right? To prove that whatever is happening on one side is also happening on the other side. So another challenge is privacy, right? So with privacy, basically the challenge with this is, let's say we take a system where you have some kind of privacy protocols. You have 5 coins going in, and then you have 5 coins coming out, right? And let's suppose that orange withdraws. So orange over here withdraws at the bottom. The big question is, which of the 5 actors at the top do we try to prevent from withdrawing, right? And the challenge is, like, in this context, we actually do not know, right? In this kind of context, like, we could try to say, let's make a parallel UTXO thing, and then we just map the bottom to the top. But then the problem is, you're not providing full security here, because you're, like, if orange withdraws, orange is basically stealing a coin from blue, right? So this is a limitation. Basically the challenge is, like, how do you actually get past this? Now, INTMAX actually does solve these problems. And INTMAX is not a pure plasma. INTMAX is a hybrid rollup plasma, so it does put about 5 bytes on chain for every single transaction, right? And the benefit that you get from this is basically you get just enough extra ability from having data going on chain that, like, you can solve these kinds of problems, and you can even get stronger properties in terms of what happens if the operator disappears, right? So it's easier for INTMAX to be permissionless than it is for regular plasma. Regular plasma can't be permissionless because you have to trust the operator, at least somewhat, not to go offline. If the operator goes offline, nobody loses their money, but everyone has to go back to L1 and everyone has to pay fees. So this is another limitation. So what are some of the conclusions here, right? Basically, one of the ways to think about plasma is I think about plasma as a way of adding extra guarantees to existing EVM validiums for free, right? So a lot of the Ethereum L2 rollup providers that we see today, a lot of them are already taking a hybrid approach, right? They're basically saying, we operate one version, which is a rollup, and then we operate another version, which is without on-chain data availability, right? So, you have Arbitrum, you have Arbitrum Nova, you have Polygon zk-EVM, and so on and so on. Now, the version with off-chain data is always going to be less secure than the version with on-chain data, because you just get so much extra security from having the data be directly there. But there's this interesting question of, like, how much extra security can you actually get while still having your data on-chain and having super cheap transactions as a result of data being on-chain. So the way that I think about these plasma ideas is basically, so if you're an L2 and you have data off-chain, step 0, this is like, you can build it, but it's not that, and this is what exists, but they're not that interesting, is that you're just a multisig, right? And, like, you have to trust the multisig. Step 1 is you become what's called a validium. Validium means you have zk-SNARKs going on chain that are proving the execution. If you become a validium, then you cannot steal people's money, but you can still disappear and freeze people's money. Step 2 is, well, if you take a validium, then you ask the question, well, if the operator does disappear, and then you have some money that is frozen, what if you can look at the information on chain and you can do a little bit more analysis and you can try to figure out, in most of those cases, how do you actually can you actually figure out what is the one unique owner of at least some of those frozen coins? And it turns out that in most cases you can. In most cases, this is actually very easy, right? Because most coins that are on chain are coins that have not moved within a week. And so even if you have an incredibly simple thing where all it does is it basically says, if you want, you can try to withdraw using old state, and if nobody challenges you for a week, then you get the money. If this is all you add, then this already is reducing the security risk of a Validium by about 90%, right? And then you can keep going, and as it turns out, even with an EVM Plasma, the amount of situations where people are still at risk just continues dropping and continues dropping, right? So basically, Plasma is something that you can layer on top to all of these systems that already exist in order to make them even more secure. This does all depend on ZK, right? So this does all depend on using zk-VM proving systems instead of optimistic ones, but ZK proving systems are improving quickly. So this is one way to think about the applicability of Plasma to Ethereum. A totally different approach is, of course, what Leona is going to talk about much more, which is Plasma for privacy, right? And some of these hybrid designs that can basically get a lot of the benefits of much greater scaling. Basically, for a rollup, the theoretical minimum amount of data that you need to put on chain, even for a non-privacy preserving transaction, is about 23 bytes. And then for privacy preserving, I think it's either 48 or 64 bytes. And with Plasma, you could go down to 5 bytes on chain, right? And so 10 times more scalability, but also still keeping some very strong properties, right? And I think this is a design space where there's a huge amount of value, right? Ethereum needs scalability. Ethereum is getting scalability, but at some point, there's going to be way too many users, even for theoretically perfect data availability in blobs, and we have to go even further, right? And to me, Plasma is the thing that can really make a dent in actually solving that problem. So I really hope that people here can continue to do Plasma research, continue to build better Plasma designs, and we can continue having a much more secure Ethereum. Thank you.